The Shapley value and the Nash bargaining solution. One of the problems with the notion of core in cost-sharing games is that it rarely assigns a unique cost allocation to a game. As illustrated in example 15.4, the core of a game is often either empty, making it useless in deciding how the cost of a service should be shared among the agents, or contains more than one point, making it necessary to have a second criterion for choosing a cost allocation. In this section, we study a solution concept called the Shapley value that assigns a single cost allocation to any given cost-sharing game. We also discuss a solution concept known as the Nash bargaining solutions for a somewhat different but related framework for surplus sharing. In both cases, the solution concept can be uniquely characterized in terms of a few natural axioms it satisfies. These theorems are classical examples of the axiomatic approach in economic theory. Both the Shapley value and the Nash bargaining solutions are widely applicable concepts. For example, applications of the Shapley value in combination with the Maulin mechanisms to multicasting is discussed elsewhere in this book. See section 14.2.2. Also, the Nash solution is related to Kelly's notion of proportional fairness, discussed in section 5.12, and the Eisenberg-Gale convex program of section 6.2. The Shapley value. Consider a cost-sharing game defined by the set A of n agents and the cost function C. A simple way of allocating the cost C of A among all agents is to order the agents in some order, say A1, A2, A3 until AN. Then proceed in this order and charge each agent the marginal cost of adding her to the service set. In other words, the first agent A1 will be charged her standalone cost C of the singleton set A1. The second agent A2 will be charged for the cost of C of the set A1, A2 minus C of the singleton A1, and so on. This method is called an incremental cost sharing. A problem with the method described above is that it is not anonymous, i.e., the orderings of the agents makes a difference in the amount they will be charged. The Shapley value fixes this problem by taking a random ordering of the agents picked uniformly from the set of all n factorial possible orderings and charging each agent her expected marginal cost in this ordering. So since for any agent I, which is in A, and any set S, which is subset equals to A minus the singleton I, with the size capital S equals to the number little s, the probability that the set of agents that come before I in a random ordering is precisely capital S is little s factorial times n minus 1 minus s factorial, then divided by n factorial. The Shapley value can be defined by the following formula. For each agent I, phi I of C is equals to the multiplications of two summations. The first summation is the term of the summations of s factorial times n minus 1 minus s factorial divided by n factorial, where s is indexed starting from 0 to n minus 1. The second summation is summations of C of S union the singleton I minus C of S, where the sum is summation is summing for all S, which is the subset equals to A remove the singleton set I, and where the size of the capital S is equals to little s, and where the phi I of C indicates the cost share of I in A in the cost sharing game AC. Like what we have discussed about the cost sharing game before. And as the following example shows, the cost sharing given by the Shapley value need not be in the core of the game even if the core is non-empty. Example 15.24. Consider the facility location game defined in example 15.2. The Shapley value in this game are as follows. Phi A, phi B, phi C. The calculations of phi A is 1/3 times 4 plus 1/6 times 3. plus 1/6 times 4 plus 1/3 times 4, which is equals to 23 divided by 6. VB is equals to 1/3 times 3 plus 1/6 times 2 plus 1/6 times 1 plus 1/3 times 1, which is equals to 11 divided by 6. VC is equals to 1/3 times 3 plus 1/6 times 3 plus 1/6 times 1 plus 1/3 times 2, which is equals to 7 divided by 3. So this cost allocation is not in the core of the game, since VB plus VC is equals to 25 divided by 6, which happens to be greater than 4, and 4 happens to be the values of the output of C of the set BC. This is despite the fact that, as we saw in example 15.4, the core of this game is non-empty. However, for submodular games, it is known that any incremental cost sharing, and therefore the Shapley value, which is a linear combination of incremental cost sharing methods, is in the core of the game. In fact, it can be shown that in this class of games, the Shapley value is cross-monotone. See exercise 15.2, making it useful in the design of group strategy proof mechanisms using Maulin's mechanisms of section 15.3. This is used in section 14.2.2 of this book in application to the multicast problem. Many other applications of the Shapley value, as well as various generalizations to settings such as NTU games or games with non-binary demands, are extensively studied in the economic literature. 15.6.2, an axiomatic characterization of the Shapley value. In his original paper, Shapley introduced what is now known as the Shapley value as the unique value satisfying the three properties defined below. Definition 15.25. Fix a set A of n agents. A value is a function that assigns to each cost function C a vector phi of C, which is defined in R to the n of non-negative numbers. Three properties of values are defined as follows. Anonymity, changing the names of the agents does not change the cost shares. Formally, phi satisfies anonymity if for every permutation pi of A and every cost function C, phi pi of C is equals to phi I of C for every I which is in A. Another property is called dummy. An agent who does not add to the cost should not be charged anything. More precisely, if for every set S which is a subset of A removing the only singleton I, C of S is equals to C of S union the singleton I, then phi I of C is equals to 0. The third property is called additivity. That is, for every two cost functions C1 and C2, phi of C1 plus C2 is equals to phi of C1 plus phi of C2, where C1 plus C2 is the cost function defined by C1 plus C2 of S equals to C1 of S plus C2 of S. So theorem 15.26 is the Shapley value is the unique value satisfying anonymity, dummy, and additivity. The above theorems whose proof is omitted here is an example of the axiomatic method in the economic theory, whose goal is to find or prove the non-existence of solution concepts that satisfy certain sets of desirable axioms, or characterize non-solution concepts in terms of axioms they satisfy. Two other prominent examples of axiomatic results are Nash's theorem on bargaining presented in the next section. This result is considered a starting point for the axiomatic approach in economic theory, and the errors in possibility result in the social choice literature. One example where this framework is applied in computer science is the axiomatic characterization of the PageRank algorithm for ranking web search results. The Nash bargaining solution. The bargaining problem studies situations where two or more agents need to select one of the many possible outcomes of a joint collaboration. Examples include wage negotiation between an employer and a potential employee, or trade negotiation between two countries. Each party in the negotiation has the option of leaving the table, in which case the bargaining will result in a disagreement outcome. More formally, a bargaining game for two players, the case of more players is similar, is given by a set X, which is defined in R to the square, that is the rational number to the square, along with a disagreement point D in X. Each point in X corresponds to one outcome of the bargaining and specifies the utility of each player for those outcomes. The point D specifies the utility of each player for the disagreement outcome. As adding or subtracting a value to the untidy utility of an individual does not change her relative preferences. We assume without the loss of generality that D is equal to 0, 0. And furthermore, we assume that the set X is convex and compact. Note that convexity of X is without loss of generality, if an outcome is allowed to be a probability distribution over pure outcomes. Furthermore, we assume X contains at least one point whose coordinates are both positive, i.e. both parties have some incentive to negotiate. The above model for bargaining was first defined and studied by Nash. Note that an NTU cooperative game can be considered an extension of the bargaining model, where in addition to the outcome of individual deviations, the disagreement point, the outcome of group deviations are also given. Nash's bargaining theorem gives a characterization of a solution for the bargaining game in terms of the axioms it satisfies. Formula is that definition 15.27, a solution for the bargaining game, also known as a social choice function, is a function that assigns to each set X satisfying the above properties a single property phi of X, which is in X. We define the four properties of a solution as follows. Pair to optimality. Phi of X is a pair to optimal, so point in X, i.e. there is no point P in X, with P greater than phi of X, coordinate-wise. The second property is called symmetry. If the set X is symmetric, then phi of X is equal to u, for example u which is a rational number. Third property is called the scale independence. The solution is independent of the scale used to measure individual utilities. If X prime is obtained from X by multiplying all utilities of the I player by lambda I, then phi of X prime can be obtained from phi of X by multiplying the I coordinate by lambda I. The fourth property is called the independence of irrelevant alternatives. If Y, which is a subset of X, and phi of X is in Y, then phi of Y is equal to phi of X. We now state Nash's bargaining theorem. The proof of the theorem is simple and is omitted here, so we just mention it. Theorem 15.28. There is a unique solution for bargaining games satisfying parity optimality, symmetry, scale independence, and independence of irrelevant alternatives. This solution assigns to each set X a point U1, U2, maximizing U1 times U2. Nash's theorem gives one example of what is called a collective utility function. A collective utility function is a function that aggregates the utilities of individuals into a single number indicating the utility of the society. Classical example of collective utility functions are the utilitarian function, which simply adds up the individual utilities, the egalitarian function, which takes the minima of individual utilities, and the Nash function, which takes the product of the utilities. So in this chapter, we reviewed some of the basic notions such as the core, cross-monotonicity, group strategy proof mechanisms, Shapley value, and the Nash bargaining solution, and the classical results on cost and surplus sharing We observed that the algorithmic questions regarding computing cost shares are closely tied to the LP formulation of the corresponding optimization problems and explains how standard LP-based techniques developed in the fields of approximation algorithms can be used to tackle such questions. There's also a potential for contributions in the other directions for many combinatorial optimization problems thinking in terms of the cost-sharing problem, i.e. the dual problem, instead of the primal can shed new light on the problem. In the facility location example discussed in section 15.4.2, the proof of theorem 15.21 gives an approximation algorithm different from the standard primal dual algorithm for the problem. As it turns out, in this case, the algorithm was known before, but theorem 15.21 gives a new primal dual interpretation of this algorithm. For the Steiner first problem, the search for a cross-monotonic cost-sharing scheme has resulted in a new two-approximation algorithm and a stronger LP relaxation for the problem. In fact, for most combinatorial optimization problem, LP 15.2 is at least as strong an LP formulation as the standard LP relaxation, i.e. it gives at least as good a lower bound result on the values of the optimal solution. These LPs are equivalent for some problems, as we saw in section 15.2.2 for the facility location problem. However, for many other problems, such as the well-studied symmetry problem, this appears not to be the case. Therefore, one possible approach to obtain stronger LP relaxations which could lead to better approximation algorithms for such problems is to start from a 15.2 and try to relax this program into one that can be solved in a polynomial time. In the case of the Steiner tree problem, the integrality gap of LP 15.2 seems to be related to the long open question on the integrality gap of the bidirected LP relaxation of this problem. In another way, the economic approach to cost-sharing can contribute to the theory of algorithms is by providing new perspective and new problems. For example, the axiomatic approach explained in section 15.6 seems to be a suitable tool for studying properties of heuristic algorithms. One notable example is the axiomatic characterization of the popular web ranking algorithm PageRank. Also, the field of combinatorial optimization almost exclusively deals with problems whose objective is to minimize the total cost or maximize the total benefit, which, according to the terminology introduced in section 15.6.3, corresponds to the utilitarian collective utility function. However, the field of social choice suggests other objective functions which can lead to new challenging algorithmic questions. One notable example is the Santa Claus problem, which seeks to optimize the egalitarian objective in a simple scheduling model. Also, many of the algorithmic results presented in Chapter 5 for Fisher markets, where the Eisenberg-Gale convex program shows that the market equilibrium corresponds to the point maximizing the Nash collective utility function, can be viewed in this light.